Institute of Aeronautical Engineering, Autonomous Dundigal. My name is N. Venkatsai, roll number 239518026. Subject Performance of Transmission Lines and Cables. Subject code AAAD18. Topic Design of HVDC Transmission Systems for Cross Border Power Transfer. Department Electrical and Electronics Engineering. HVDC for Cross Border Power Transfers. Why HVDC? The imperative for interconnected grids. High voltage direct current transmission has become essential for modern power system seeking to interconnect grids across borders and integrate renewable energy at scales. Unlike traditional AC systems, HVDC offers superior efficiency over long distance, low transmission losses, and enhanced control capabilities that are critical for stable, reliable power distribution in increasingly complex energy landscapes. Lower losses. HVDC reduced transmission losses by 3 to 5% compared to AC over long distances, translating to significant cost savings. Enhanced control. Independent control power grid and voltages enables precise grid management and stability loss across borders. No reactive power. DC transmission eliminates reactive power requirements, reducing infrastructure cost and improving efficiency. HVDC system technologies LCC versus VSC and their applications. Two primary HVDC technologies dominates modern designs: line commutated converters systems and voltage source converters systems. LCC technology, the mature workhouse of HVDC, excels in high power long distance applications with excellent cost efficiently. VSC technology, more recent and increasingly prevalent, offers superior grid support, reduced harmonic disruption, and the ability to operate independently from strong AC grid, making it ideal for renewable energy integration and offshore applications. LCC technology, proven reliability with decades for operational history, higher power capacity and lower converts losses, cost effective for long distance bulk power transformers, requires strong AC systems for communication. VSC technology, independent power control and grid supported capability, low harmonic destruction and compact design, ideal for renewable integration and weak grids, growing cost competitiveness in shortest distance. Key design consideration: power rating, voltage levels, and cable selections. Designing an HVDC interconnections requires careful optimization across multiple parameters. Power rating typically range from 500 kilowatts to over 12 watts, determined by projected cross-border power flows, a system reliability requirements, voltage levels. Commonly 400 kilowatts, 500 kilowatts or 800 kilowatts balance cost losses and right of the containers. Capable and transmissions line selections depends on distance, environmental conditions and whether the route is overheated and submarine. Power rating selection determined by load forecast, renewable capacity and cross-border trade potential. Large rating reduce per unit cost but require more robust infrastructure. Voltage optimization. Higher voltages reduce losses and lines cost but increasingly insulation requirements and environmental concern. Engineering analysis balance technical and economical trade-offs. Transmission routes. Overhead lines shoot long continuous crossings. Submarines capable cross water waves capable technology cooling systems and installation methods significantly impact project feasibility and cost. Grid integration challenges, AC to DC interactions and control strategies. Integrating HDVC links into predominantly AC grids introduce complex interactions requirement sophisticated control modern strategies employ voltage source converters with fast frequency response, phase locked loops synchronization, and adaptive protection schemes. This technical ensures seamless power flow management while maintaining voltage stability and supporting grid frequency during transition and faults. First, harmonic destruction mitigation. Filters and advanced modulation techniques minimize harmonic injections into adjacent AC systems, protecting sensitivity equipment and maintaining power quality. Frequency and voltage support. VSC technology enable inertial response and voltage supports independent of AC source strength critical for system with high renewable penetration. Coordinated control architecture, multi-level control hierarchies, local converters control system-wide supervisory control, and market-based dispatch ensure reliable, efficient operation across borders. Protection and reliability, ensuring system stability and fault management. HVDC transmission systems requires comprehensive protection schemes to detect and isolate fault while maintaining overall grid stability. DC circuits breakers developed over the past decades now enable effectiveness protection without the natural current. Zero crossing found in AC system. Multi-terminal HVDC network presents additional complexity, required selective protection algorithms that prevent cascading failures. Reducer in converter strains, coordinated AC and DC protections, and real-time monitoring systems are essential components, ensuring high availability and rapid fault recovery. DC circuit breaker technology. Hybrid DC breakers combine mechanical and semiconductor switching to interrupt fault currents and microseconds, protecting cables and converters from thermal damage. Multi-terminal protection. Selective protection algorithms ensure fault isolate to minimal system selections, preventing widespread blackouts while maintaining power transfer or healthy circuits. Environmental and economic impact of HVDC interconnections. HVDC interconnections deliver sustainable environmental and economic benefits to intraconnected region by enabling efficient renewable energy transfers across borders. HVDC links facilitate higher penetrate of wind and solar resources, reducing greenhouse gas emissions. Economic impact include reduced electricity costs through upgrade and across to larger, more diversified energy markets. However, projects must address environmental concerns including visual impact of transmission corridors, electromagnetic field explore and disruption, comprehensive environmental assignments, community engagement of comprehension framework are essential for social license and protect success. 30% of typical CO2 reduction from increased renewable energy penetration enabled by HVDC interconnection. 15 to 25% of cost reduction. Potential electricity price decrease from cross-border energy trading to optimization. 5 to 8% of transmission loss savings compared to equivalent AC transmission over long distance. Case studies successful cross border HVDC projects. Global HVDC deployments demonstrate proven capability for international power interconnections. The Quickbay New England LECC links has reliability transformed hydropower for over 35 years. Europe's HVDC corridor Newton connections Scandinavia's hydropower with conventional industrial centers. Brazil Meridian Link successfully combines the high power capacity with long underwater cable crossing. This project showcases diverse converts technologies operating environmental and regulatory frameworks. Each project contributes operational experience and technical innovations that inform current and future interconnection designs. FIBI New England 2 lakhs 250 milliwatts LECC links delivering Canadian hydropower since 1918. Not bad. 700 milliwatt VSC submarine cable connection Lithuanian and Sweden. Meridian link 6300 milliwatts LCC systems with 2385 kilometers submarine cable in Brazil. 2050 milliwatts. Future trends hybrid HVDC systems and offshore grids. The next generation of HVDC technology promises a revolutionary advance in grid interconnections. Hybrid AC DC systems combine benefits of both technologies. Optimizing efficiency and control. Multi-terminal HVDC networks enable complex power routing across multiple countries and renewable sources simultaneously. Floating offshore wind farms connected via VSC HVDC submarine cables and sand farm renewable energy accessibility. Modular converters designed reduce manufacturing cost and accelerate deployment. Artificial intelligence and machine learning enhance predictive control and optimizing complex network operations. These innovations will enable deep decarbonization while maintaining grid reliability in the increasingly distributed, renewable dominating energy landscape. Multi-terminal networks. Hub and spoke HVDC architectures enabling optimal power routing across multiple border and source. Offshore grids, dedicated submarine HVDC networks connecting offshore wind to distributed onshore load centers. Sustainability integration, seamless renewable energy integration supporting 100% of decarbonized electricity systems. Modular converters, standardized scalable converter designs reducing cost and enabling rapid technology deployment. AI power controller, machine learning algorithms optimizing real-time power flow, predictive grid management. Conclusion, realizing an resilient and integrated power future, HVDC transmission technology has evolved from specialized applications to essential infrastructure for the modern energy transition. As nation pursues ambitious decarbonization goals and renewable energy integration, cross-border HVDC interconnections provide the technical foundations for efficient, reliable, cost-effective power exchanges. Continued innovations to innovative technology, control systems, and protections. Scheme will enable increasing complex multi-terminal networks that optimize renewable resource globally. Success requires coordinates policy frameworks, investment in grid infrastructure, and commitment to technical excellence. HVDC represents not merely transmission technology, but the physical embodiment of an integrated, sustainable, and realistic global electricity system. Today, mature LCC and VSC technologies enabling reliable long distance power transfer, near term expansion of multi terminal networks, and floating offshore wind integration. Future AI optimized, fully decarbonized, globally integrated HVDC based electricity infrastructure. Thank you.